Welcome, welcome, welcome. This is the first edition of our Pandemic PDEs course, and this is going to basically be a set of videos, which is just the digital overheads, and we've got a few topics to get through before we end off this year. I'm going to pick up where we left off, and we were dealing with LaPlace's equation on something like this, on a circle. And we had a radius r0, and so we can characterize this circle easily in polar coordinates, but not so easily in Cartesian coordinates, obviously. So we could just say r is equal to r0, and theta is equal to 0 up to 2 pi. And in that way, we can characterize the boundary of this region, as opposed to the difficulty in defining the boundary in Cartesian coordinates. We went down last class and we said, okay, if we want to switch into polar coordinates, we've got to go x equals r cos theta, y equals r sine theta, and then our task is to convert uxx plus uyy equals 0 into its polar coordinate version. And so we need ux, u sub x, and we need u sub y. And this is the derivative with respect now to r and theta. So we have the derivative of u with respect to r times the derivative of r with respect to x, and then the derivative of u with respect to theta, derivative of theta with respect to x. And similarly, we have the y derivative, u with respect to r with respect to y, and u with respect to theta, theta with respect to y. Now, u sub r, u sub theta, those are things that we might expect to appear in the final equation. But we needed the derivative of r with respect to x and y, and derivative of theta with respect to x and y. And we did some work last class to obtain that, and we ended up with expressions for these two things. So the derivative operator with respect to x turned out to be derivative with respect to r, and then we multiply by cos of theta. That is, the derivative of r with respect to x is cos theta. And then we have minus the derivative with respect to theta, and then this turned out to be sine theta over r. We did some matrix methods to obtain these. Derivative operator with respect to y turned out to be the derivative with respect to r times sine theta, and then the derivative with respect to theta, and then cos theta over r. So we derived all that last class, and now we want to apply this to calculate uxx and uyy, fill in that Laplace equation and see what we get in the new polar coordinates. All right, so this is actually a little bit long, a little bit detailed, but we'll do it anyway. What the hell? Where else do we have to be? The derivative of u with respect to x, nested twice, is applying this derivative operator already to the derivative of u with respect to x, which is the derivative with respect to x of, well, we've got it written up there, derivative of u with respect to r, and then we multiply by cos theta, minus derivative of u with respect to theta, sine theta over r. My dog's looking at me. I don't know what to tell him. All right. Now I apply the x derivative operator again on this new argument, on this argument here. Okay? I'll get rid of that. It looks confusing. All right. So it's the derivative with respect to r of this thing, of all this, which I'll write as u r cos theta minus u sub theta sine theta over r. And that term gets multiplied by cos theta. So I've applied the first part. And then I have minus the derivative with respect to theta of that same expression. U r cos theta minus u sub theta sine theta over r. And that gets multiplied by sine theta over r. All right, so there it is, nested twice. And when you multiply all this through and clean it up, you get u r cos theta minus u theta r sine theta. We got a cos theta, that's over r, plus we've got a u theta, u sub theta, sine theta cos theta over r squared. Got a minus sine theta cos theta over r u sub r theta. Oh, goodness gracious, we're still going here. Plus the derivative of u with respect to r sine squared theta over r. And now, just to keep you up to speed, we're dealing with this fella now. So it's the derivative of theta with respect to, with the derivative of that term with respect to theta, which is going to feed us a u sub theta theta, second derivative of u with respect to theta, sine squared theta over r squared, and then finally we have the derivative of u with respect to theta, cos theta sine theta over r squared. You might think this is going nowhere fast. A small bit of cancellation occurs. Specifically, where is it? Yeah, I mean, there's two of these things. There's one there and there's one there. They're the same. You can assume those mixed partial derivatives are equal. And so, what do I get? U sub r cos theta minus 2u sub r theta sine theta cos theta over r plus 2u sub theta sine theta cos theta over r squared plus ur sine squared theta over r plus u sub theta theta sine squared theta over r squared. Well, wonderful, beautiful. We had better hope for some really judicious cancellation coming on with u sub yy. Otherwise, this is just horrendous, and you can't imagine any method working on this, like separation of variables. Similarly, we can show, if we do this double application of this derivative operator with respect to y, we can show that u sub yy, the second derivative of u with respect to y, is equal to u sub rr sine squared theta plus 2u sub r theta sine theta cos theta over r. Well, that looks kind of nice, because look, get my lightsaber out here, minus 2ur theta sine theta cos theta over r, and there's plus 2. Oh, so a little bit of help there. That's nice. What else do I got? Minus 2u sub theta sine theta cos theta over r squared. Also nice. Plus that stuff minus that stuff. We have a plus u sub r cos squared theta over r. Well, that's not canceling. And then we have a u sub theta theta cos squared theta over r squared. So right now I'm seeing some definite cancellation. I'm seeing some sine squareds and cos squareds. And so, yeah, maybe we'll get somewhere. When I join them together, uxx plus uyy, and factor out a few common terms, you end up with u sub r. And I'm realizing I forgot a... Yep, look at this fella up here. This is good old math for you. Derivative of this thing right here with respect to r is going to give you u sub r in the first term, cos theta, and then there's a cos theta over here. I forgot to multiply them together. There's a squared in there. You're going to walk down, go there, and that means that the second derivative of u with respect to r that we're seeing a couple times here, there, and there, when we add them together, I get a cos squared theta and a sine squared theta that I can factor out. All right, I'm back on board here. So, sine squared theta plus cos squared theta. Oh my god, that might be equal to something nice and simple. I have a u sub r over r. There it is, yep. I also get a sine squared theta and a cos squared theta. Nice. Those middle terms cancel out with the mixed partial derivatives. And then I have this plus u sub theta theta over r squared, also with a sine squared theta plus cos squared theta. Okay, and again, when I add them together, that and that and that and that are going to cancel. Sine squared theta plus cos squared theta, you might know this, it's equal to 1. Isn't that interesting? So I get, finally, u sub r times 1 plus u r over r, derivative of u with respect to r divided by r, plus u sub theta theta over r squared equals 0, because obviously Laplace uxx plus uyy equals 0. That's formulation. So it took a little bit of doing, but we got here. This equation is Laplace's equation in polar coordinates.